Dear students, today I am going to give a class from Chemistry First Paper, Chapter 3. Chapter name is Periodic Properties and Bonding in Elements. My topics periodic properties, contents, atomic size, ionization energy, electron affinity, electronegativity, and melting and boiling point. First of all, atomic size. Atomic size consider the distance from nucleus to valence shell. In this slide, we can see the elements of third period. We can each element contain three energy level. From sodium contain 3 energy level, and outermost shell contain only third energy level contain 1 electron. In case of magnesium, third energy level contain 2 electron. In case of aluminum, third energy level contain 3 electron, and in silicon, third energy level contain 4 electron. In phosphorus, third energy level contain 5 electron, and so on. That means no new shell is added, but only 1 electron is added. Since 1 new electron is added, that means nuclear charge is also increases from left to right, so that attraction of nucleus on valence shell is also increases. For that, total atomic size is decreases from left to right. Now, in this, that is the elements of group 17, where fluorine contain 2 energy level, but chlorine contain 3 energy level, bromine contain 4 energy level, and iodine contains 5 energy level. That means new energy level is added. So, summary is that from left to right, atomic size decreases, and from top to bottom, atomic size increases. Our next topic is ionization energy. Ionization energy is also depends on the atomic size. Basically, atomic size is main base on depending on atomic size, ionization energy properties also changes. Definition is the amount of energy necessary to remove 1 mole of electrons from outermost orbit of an 1 mole gaseous element to form 1 mole unipositive ions is called ionization energy. Now, if we represent this ionization energy in a chemical reaction, M is a atom which release 1 mole electron and converted into 1 mole unipositive gaseous ion. Factors of ionization energy: first, increase of atomic size decrease ionization energy. Next, increase of suborbit increase ionization energy. Next, half or fully filled orbital has high ionization energy. From these three characteristics or three factors, total summary is ionization energy increases from left to right and decreases from top to bottom. That is the general rules. It is the total graphical representation of ionization energy. From this total graphical representation of ionization energy, we can see helium has highest ionization energy. Since why? Since helium placed at the right side of the periodic table and top of the group, so helium has high ionization energy. Now, ionization energy of beryllium and boron. Beryllium placed in group 2 and boron placed in group 13. We know from left to right, ionization energy increases. That means since boron is placed in right position comparing with beryllium, so that boron ionization energy of boron should greater than beryllium, but from the electronic configuration we can see that beryllium has fully filled outermost shell. But boron has no fully or half-filled outermost shell. Since beryllium has fully filled outermost shell, so it is difficult to remove one electron from beryllium. That is the exceptional in this exception, that is the exception. In this example, beryllium has higher ionization energy than boron. Although according to general rules, we know that ionization energy increases from left to right, but in case of beryllium and boron, it is different. Now, electron affinity. Definition: the amount of energy released when 1 mole electron is added to 1 mole of neutral gaseous atom of an element to produce 1 mole uni-negative gaseous ion is called electron affinity. Chemical representation: A is a neutral atom which accept 1 mole electron and convert into 1 mole uni-negative gaseous ion. Now, factors: increase of atomic size, decrease of electron affinity. Next, increase of nuclear charge, increase electron affinity. Increase of electron density in valence shell, decrease electron affinity. From these three factors, total summary is that from left to right, electron affinity increases, and from top to bottom, electron affinity decreases. That is the general rules of electron affinity. But there are some exceptions, like electron affinity of fluorine and chlorine. We know from top to bottom, electron affinity decreases. That means fluorine is top position considering chlorine. So, fluorine should higher electron affinity than fluorine, but in case of fluorine, we can see it has second energy shell. That means only 2 energy shell, and outermost shell is second energy shell. And in chlorine, it contains total 3 energy shell, and outermost shell is third energy shell. In second energy shell, fluorine contains 7 electrons, and in third energy shell, chlorine contains similarly 7 electrons. So, in fluorine, it is difficult to stay 7 electron in second shell comparing to third electron of third orbital of chlorine. It is easier to stay 7 electron in third energy shell, since third energy shell is larger than second energy shell. So, in case of fluorine, there increase the density of electron, so that electron affinity of fluorine is lower than electron affinity of chlorine. That is another exception in case of electron affinity. Next topics: electronegativity. The tendency of an atom to attract a shared pair of electrons toward itself. Since it says shared pair of electrons, that means electronegativity is the property of covalent compound. Factors: increase, that means electronegativity increase along period, electronegativity decrease along group, and so fluorine is more electronegative element in the periodic table. Now we consider a covalent compound, hydrogen fluoride. We can say that hydrogen is poor electron region, but in the site of or the surrounding of fluorine is the high rich electron rich region. That means bonded electron is attracted by fluorine, or fluorine attract the electron cloud towards itself, okay, due to the property of electronegativity. Next, melting and boiling point. Melting and boiling point. When solid convert into liquid, that is called melting point, and when liquid convert into gas, that is called boiling point. That is the general chemical reaction we know, and that is total representation of graphical representation of melting and boiling point of third elements of third period. From this graph, we can see that silicon has higher melting point, but melting point is increases gradually, and silicon gives higher melting point, and suddenly the graph is fall in case of phosphorus. That means phosphorus has lower, again it rise up in case of sulfur. Why this variation is occur? Silicon has high melting point. Why? Because one silicon is bonded, that is the silicon net or silicon bond net. In this structure, one silicon is bonded with 4 silicon. So each silicon is bonded with 4 silicon. Thus silicon bond form a giant compound of silicon crystal. So it require high energy to break one silicon atom. Next, in case of phosphorus, it is decreases gradually. In this graph, we can see in case of phosphorus, melting point is decreases gradually. Why? Comparatively, silicon, only one phosphorus is added with 3 another phosphorus in P4 molecule. So if we want to break a phosphorus bond, so we need to break up 1, 2, 3, only 3 bond. Next, sulfur. Structure of sulfur. One sulfur is bonded with 2 sulfur, and that is the structure of sulfur S8 molecule. Structure of sulfur S8 molecule. Another structure is ring structure. One sulfur is also bonded with another 2 sulfur. So for that melting and boiling point decrease gradually, less than melting and boiling point is less than silicon. Now, questions from my lecture. Between beryllium and boron, which has higher ionization energy? Between chlorine and fluorine, which has higher energy, electron affinity? And which element has high ionization energy in periodic table? Which element has high electronegativity? Please write down your answer in comment box. Thank you.